Join me as I tackle the challenge of breaking down the photoelectric effect in a way that's super easy for you to understand, even if you're just starting out in grade 12 physics. Classical physics had a hard time explaining the photoelectric effect, and that's because it couldn't account for why light's intensity alone couldn't eject electrons from a metal surface. The more intense the light, the more electrons were expected to be ejected. But that's not what happened. Experiments showed that even in low-intensity lights, electrons could be ejected as long as the frequency was high enough. So let's move on to solving this problem, and we're going to do so with the equation for the photoelectric effect, which says that the kinetic energy of the ejected electrons is equal to the energy of the photon, which is h Planck's constant times the frequency of the photon minus the work function of the metal. So in this question we have orange light that has a wavelength of 600 nanometers, is directed at a metallic surface with a work function of 1.60 electron volts. Find the maximum speed of the emitted electrons. So in this case we're given wavelength, not frequency, but that's okay because we can use the wave equation, which is the speed of light is equal to its frequency times its wavelength. If we rearrange this for frequency by dividing both sides by wavelength, we get c over lambda. So we can replace that in this equation. So we'll have hc over lambda minus the work function. So let's put in our values so that we can figure out what the kinetic energy is of these ejected electrons. So we have Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. And then multiply that by the speed of light in a vacuum, so 3 times 10 to the 8 meters per second, all divided by our wavelength, but we have to convert this back into meters, so this is going to be 6 times 10 to the minus 7 meters. Okay, so a nanometer is 10 to the minus 9, so that means 600 nanometers is 600 times 10 to the minus 9 meters, and then I just move that decimal place over 2, so I write it in scientific notation, and then I add 2 to our exponent, bringing it from minus 9 to minus 7. Then we have to subtract the work function, so we subtract 1.60 electron volts. But the problem is that this value here, hc over lambda, is going to give us a value in joules. We can't then subtract another value in electron volts. So we're going to have to convert electron volts into joules, and we're going to do so by multiplying by the conversion factor 1.602 times 10 to the minus 19 joules per electron volt. So that's going to give us our work function in joules. So when we plug all of that into our calculator, we get 7.50 times 10 to the minus 20 joules. Now if we want to figure out the maximum speed, we're just going to set kinetic energy equals to 1/2 mv squared. And that mass is the mass of an electron. So if we multiply both sides by 2 and divide by mass, we'll get v squared equals to 2 times 7.5 times 10 to the minus 20 joules, all divided by mass, and that's the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. And take the square root of both sides. We're going to do this over here because I'm running out of room. The speed then is equal to 4.06 times 10 to the 5 meters per second. Well, I hope that has helped you. Thanks for watching, and don't forget to leave a comment below about your thoughts and any questions you might have about the photoelectric effect. And if you're interested in learning more about high school physics, be sure to check out my other videos.